Hello everyone, I'm Inderjeet Singh from Secure System Research Laboratories, NEC Corporation, Japan. I'm presenting our paper on powerful physical adversarial examples against practical face recognition systems. Our goal is to strengthen physical attacks for real-world risk assessment of practical face recognition systems. We propose a novel smoothness loss and a patch noise combo attack method. Motivations for this work. Traditional smoothness loss suffers from the problem of causing less controlled smoothness constraint on the adversarial optimization process. Traditional smoothness loss also does not allow selective smoothing inside the adversarial noise region for complex real-world patterns. Conventional adversarial patch attacks do not consider combining adversarial noise generated considering different constraints for a powerful physical attack. Now, what are adversarial examples? An adversarial example is an instance with small intentional feature perturbations that cause a machine learning model to work in a certain false way to achieve adversary's objective. The figure shows that when an adversarial image added with an adversarial eyeglass is fed to a target machine learning model, that image is misclassified as target image identity. Early works in adversarial machine learning studied adversarial examples in the digital space only. In this work, we focus on physical adversarial examples under the physical image registration attack setting. Now, what is a physical adversarial example? When a digital adversarial example is transferred to the physical domain and used to attack a target system from the physical world, it is called physical adversarial example. The figures on the right side shows the use of adversarial patches for object and face ID misclassification. The attack performance in the physical world has been relatively lower than the digital world. Now, physical image registration attacks. In physical image registration attacks, an adversary submits a printed adversarial image during a registration process that causes a mistake by the target face recognition system at the inference time. The common target systems for these kind of attacks are person re-identification system, automatic ID document photo matching systems at international borders, etc. Some key terms. In practical situations, an adversary may or may not have the information access of its target face recognition systems. In this figure, face recognition system 1 is under the adversary's control, but the adversary does not have any information access about the face recognition system 2. The generated attacks against the face recognition system 1 using its complete information are called white box attacks. To attack face recognition system 2, the adversary crafts an adversarial example against the face recognition system 1 acting as a surrogate model due to similar model characteristics and then uses that adversarial example to attack face recognition system 2. This attack is called black box adversarial attack. The ability of a successful white box adversarial example to succeed on a black box model is called black box transferability. On the other hand, physical transferability is the ability of a successful digital adversarial example to fool a target system from the physical world. Now, there are some challenges for the success of physical adversarial examples. The success of physical adversarial examples primarily depends on the physical reconstruction losses. Physical reconstruction loss is the total amount of information lost and the noise added to the physical adversarial example while transferring it from the digital world. It comprises the errors due to printing, camera noises, change in camera angles, variable lighting conditions, attack surface characteristics, and the realism of the adversarial example. For a better attack performance in physical world, existing works tried reducing the physical reconstruction losses. To reduce physical reconstruction losses, existing approaches focus on generating smoother adversarial patterns. Now, existing smoothness losses. Sharif et al. Introduced a smoothness penalty which minimized the total variation. In total variation minimization, the difference in the values of the pixels of immediate pixel pairs are calculated. They increased the smoothness of the patch, thereby improving the inconspicuousness and physical realizability. However, their laws suffer from some limitations. It causes substantial smoothness constraints on the adversarial optimization process. It also restricts possible practical patterns in the generated adversarial examples. It does not allow selective optimization in the adversarial noise pixels. Our first contribution, a novel smoothness loss. We propose a smoothness loss based on an activation threshold that causes calculation of total variation only for the pixel pairs having deviation greater than the threshold from an initial reference value. This equation presents our smoothness loss. Pij is the difference in the value of a pixel from the reference value at location ij in the adversarial noise region. M is a dynamic mask that activates the smoothness loss for pixels with intensities greater than a predefined threshold matrix Z. Working difference in existing and our smoothness loss. The existing smoothness loss starts penalizing total variation right from the beginning of attack generation process, hence causing excessive regularization constraints on the adversarial optimization process. Our smoothness loss causes delayed smoothness regularization during the attack generation process due to the use of threshold-based activating mask for the total variation calculation. The use of threshold-based activating mask calculates total variation only for the noise pixels with the most active gradients, hence allowing selective optimization in the adversarial noise region. Our second contribution, a patch noise combo attack. Existing works focus on generating adversarial noise coming from a single distribution or environment of similar constraints. To generate stronger adversarial examples for face recognition systems in the registration attack setting, we combined an adversarial patch in the form of eyeglass with an imperceptibly small noise, as shown in the figure. The adversarial examples generated in our patch noise combo attack by combining the face image with adversarial noise are given in the equation. We use two different masks for the imperceptible noise as well as patch noise. To show the effectiveness of our method, we used the following experimental setting. We used 5 state-of-the-art pre-trained face feature extractors, 4 white box attack generation algorithms, and 3 black box attack transferability techniques. We conducted our experiments in the digital as well as physical worlds. Our adversarial objective was to generate impersonation attacks. For each attack combination, we generated 100 adversarial examples for the digital evaluation and a subset of 10 adversarial examples for the physical evaluation. Now, this is our physical adversarial example generation pipeline. We first generated digital adversarial examples. Then those digital adversarial examples were printed and captured using the target face recognition system's camera. While doing this, we considered different brightness levels, light color temperatures, and camera angles. Then we performed data cleaning. The clean data were then fed to the MTCNN based face detection and alignment step. Then the deep features of the cleaned, captured adversarial images and a probe image were compared, and the attack success was then checked using a distance based or cosine based similarity functions. Results for the digital adversarial attacks. The figure on the left shows the result for the white box digital adversarial examples. The figure on the right shows the results for the black box digital adversarial examples. Our smoothness loss in white box attack setting resulted in a better attack success rate compared to the adversarial examples generated from the existing smoothness loss. However, our smoothness loss performed comparatively similar to the adversarial examples generated from the without use of any smoothness penalty. On the other hand, in black box attack setting, our smoothness loss completely outperformed all the baselines. Our patch noise combo attack resulted in significantly higher white box as well as black box attack success rate for all the baselines. Results for the physical adversarial attacks. The figure on the left illustrates the results for the white box physical adversarial examples. The figure on right illustrates the results for the black box physical adversarial examples. From these two figures, we can clearly see that our smoothness loss as well as our patch noise combo attack method significantly outperforms their respective baselines. These results clearly demonstrate the effectiveness of our proposed smoothness loss and the patch noise combo attack for generating powerful physical adversarial examples. From the experimentation, we also found that the total variation present in the generated adversarial examples from existing and our smoothness loss was similar. This means that the our smoothness loss and the existing smoothness loss introduced similar amount of smoothness in the generated adversarial examples. Also, total variation in the adversarial examples generated using the smoothness regularizers was significantly lower than the adversarial examples generated without any smoothness regularizer. This means that the use of these smoothness regularizer actually introduces some smoothness in the generated adversarial examples. From our experimentation, we also confirmed that there was a significant physical transferability increase for our patch noise combo attack. We also evaluated the relation of change in the physical attack success rate and imperceptibility with the increasing size of adversarial noise to understand the effect of imperceptible noise in the physical world adversarial attacks. The results are shown in the figure on the right. We found that adversarial noise size was directly proportional to the physical attack success rate and inversely proportional to the physical imperceptibility of the adversarial examples. To conclude, this paper proposed a novel smoothness regularizer and a patch noise combo attack method for generating powerful physical adversarial examples against practical face recognition systems. Our smoothness loss allows generating much complex real-world adversarial patterns. Our patch noise combo attack provides significant physical attack success rate improvements. From physical world evaluation, we conclude that the size of imperceptible noise has a trade-off of attack success rate and physical imperceptibility. The generated digital and physical adversarial examples from our method allow an adequate risk assessment for the practical face recognition systems. Thank you very much for your attention.